morning, everyone. Myself, Mohammad Anwar Ansari. I am currently pursuing BTech in Electronics and Communication Engineering from an Alia University, Kolkata. Today, I am going to present that what I learned during my internship on the EV ADAS dashboard. During this internship, I explored how modern electric vehicles monitor important parameters such as battery status and the vehicle speed. The safety information is in real time. And I also learned how advanced driver assistance systems helps making driving safe and smart. So through this presentation, I will share the project overview, the system architecture and the development process and the skills what I learned during the internship. So let's begin. So first question is what is an EV ADAS dashboard? So EV ADAS dashboard is the main interface between the driver and the vehicle. It displays the real-time information about the vehicle's condition. It shows, it displays, and it helps the driver make safe and informed decision while driving. And it also displayed the information help the driver operate the vehicle safely and efficiently. Okay, let's move into the introduction to ADAS. What is ADAS? Which is stand for Advanced Driver Assistance System. It is also a technology that helps driver by improving safety. It improves safety and supporting better driver decision. It reduces the risk of accidents by monitoring the surrounding and providing timely warning or assistance. And what are its benefits? Its benefit is that it reduces driver stress, it prevents collision, it enhances driving comfort, and it supports smarter driving. So let's begin. Why smart EV dashboard matter? Before developing any system, it's important to understand the problem, what problem is. So modern electric vehicles generate a large amount of real-time data, including speed, battery charge, motor temperature, and sensor information. Monitoring all of this manually is difficult. An EV ADAS dashboard solves this problem by collecting and displaying all information on a single screen. It also provides safety alerts and helps the driver make better decisions while driving. Okay. So move into the system architecture. This slide show the overall architecture of the system. Different sensors collect vehicle information such as acceleration position, brake input, and the battery status, state of charge, SOC, which stands for state of charge, and the motor temperature is also there. The STM32 microcontroller processes this information and executes the AV and ADAS algorithms. Finally, this process data is sent through the UART to the Python dashboard, where all vehicle parameters are displayed in the real time. And as you can see, there is a use analog to digital converter. So this question is arise why ADC is used, because our STM32 microcontroller understand only the digital form. Okay, it does not understand the analog logic. That's why we use ADC here. Now move into the 9 phases of the project. So what things we are used during this internship development environment is which is STM32 plus PixSims lab and the Python setup. And what are the GPIO and the peripherals, LED, PWM buzzers, timer interrupts, and ADC sensor input, potentiometer, acceleration, brake, motor temperature. Uh, then we implemented the EV dynamic model, ultrasonic ADAS features, fault detection systems, UART communications, and finally developed the dashboard. Moved into the ultrasonic ADAS engine. This slide explains the ADAS features implemented using ultrasonic sensors. The system can detect nearby obstacles and provide features such as providing collision warning, blind spot detections, time to collision detections, parking assistance, and overspeed advisory. So these all features improve vehicle safety by warning the driver before dangerous situations occur. Okay, and this light fall detections and alarm priority system is there. So to improve system reliability, a fall detection mechanism was implemented, and this dashboard continuously monitored different vehicle conditions. Depending on the severity, alarms are classified into the four levels. First level is the advisory level, normal, and warning and critical. And many of them. Okay, and there is a Python dashboard dashboard. The final dashboard was developed using Python and Matplotlib to display the vehicle speed, battery state of charge, speed history, EV parameters, and the bird's eye view of the ADAS system. The dashboard updates in real time, making it easy to monitor the vehicle performance. And lastly, finally, I just showed the results and the demo. The final system successfully displayed the real-time vehicle information and ADAS alert. It was able to monitor battery status, speed, obstacle detection, blind spot monitoring, and fault condition accurately. The project demonstrated how embedded system and software can work together to build an intelligent EV dashboard. So, conclusion is that before I concluded that I am sharing such things during this internship, I gained a practical knowledge of electrical vehicle technology, embedded system, STM32 programming, UART communication, sensor integration, dashboard design, and ADAS concepts. So this experience really helped me to understand how modern EV ADAS dashboard are designed and how software and hardware work together to improve the vehicle safety and performance. Overall, this internship strengthened both my technical knowledge and my problem solving skills. Let me showing practically. Okay,
requirements. Then when we save, it will give and generate as a code that will be of name main.c, and then we will write the code needed for our project. But as the code is of too long, we will create source files and header files in which we write the codes and then call them in the main file. Then we will build the project, and during building the project, right click on the ev dash, which is our project. Then there you can see build project option, by which our project will be built. And before that, select the project to build a binary file when the project is being built. And after building a project, when there are no errors, our binary file will be created and it will be saved in the files where we have given the path to it. Then let us see the Pixim Lab. In Pixim Lab, we are using the board that is Blue Pill as per our project requirement. And here we are using the peripherals are ultrasonic sensors, VT LEDs, and a potentiometer and a buzzer. Ultrasonic sensors are used to measure distance, which is used to calculate collision times and if there are any collisions that are going to happen and predict them. LEDs are used for closeness and if crash is going to happen and fault and alarms. And the potentiometers are used because we cannot give the input to the sensors in online, so we are using potentiometers to change them as per our requirements. And then VT term is where we can observe our output in virtual, and buzzer for alarms. Then let us upload the binary file which we have created in the STM32 cube IDE. Open the file where the binary file is being created, then double tap on it. Then we can observe our outputs being printed like speed, SOC, torque, motor temperature, range, driving mode, acceleration, brake, and all those things. And this thing will be updated every 100 milliseconds. Let us change the value so that we can observe the. Let us set up this. In the front distance ultrasonic sensor, let us decrease the distance. So as you can see, when I decrease the distance, STM32 a red color LED is being on. It means there is a chance of being collision, and a fault alarm also gets here. And we can observe in the VT term output as alarm as critical. Then again, if we increase the front distance to 240, then this red LED and the yellow LED will be turned off, and the alarm status in the virtual terminal will be none. Then when the left distance is below 30, then the blue LED will be on. It is suggesting that the left side collision is going to happen, and the alarm will be advisory. And when we increase the distance above 30, the blue color LED will be turned off. Same like that for right distance. When the distance is less than 26, then a green LED will be on, and in the virtual terminal we can observe the alarm as advisory. And in the potentiometers we can increase and change the accelerations. As we can see, I have decreased the acceleration, so the speed which is increasing rate will decrease. And this is brake, used to decrease the speed. We can observe the speed being decreased from 37.5 to 37.3 and still going on. And then is the SOC. SOC it stands for state of charge. And another one potentiometer is the temperature, which is of motor temperature. And when the temperature is above 80 degrees Celsius, then the fault LED will be on, saying there is something faulty in the system, and alarms will be come, like motor is overheating fault. And when the temperature decreases to a normal range, then the yellow LED will be turned off, and the motor overheat will be not come. As we can observe in virtual terminal, before was motor overheating, now we can observe there is no such warning. Now we need to upload this data into our dashboard. For that, we will create a dashboard using Python in VS Code. Then that file will be saved. Then by opening our command prompt as administrator, we will go to the path where our Python file is, and we will print in command prompt as py/port com4. Then our dashboard will be opened, which we have created. And if we have already created comms in the VSPE, then it will automatically connect. If we have not connected the VSPE, then we have to create a VSPE so that the data is being sent from one to another. For that, we will go to virtual serial port emulator, that is VSPE, their device where we can create new devices. As I have already created, my devices are being connected. So in command prompt, we will go and enter the code as py/port com4. Then my dashboard will open, and if the comms are already created, then the comms will be connected. I have placed my blue pill as serial port as COM1, and I am taking the data to COM4. So we can observe here in my dashboard of which I have created here: speed, SOC, that is state of battery charge, and the ADAS, the distances like front distance, left distance, right distances, and EV metrics where torque, acceleration, brake, motor temperature, alarm, fault, signal, those are here, and also a graph of speed showing here. And currently my speed is 60 and SOC is 95.8, and the speed is going to increase and SOC is going to reduce. As you can see, the speed is 62. Now then, let us change the values in PiximLab and observe the changes that are going to happen in our EV dashboard. I am going to change the front distance to below 170, then I will get a red alarm saying a possibility of collision is there. So let us observe if this is being displayed on dashboard. Yes, as we can see here, the distance is less than 170 and that is 158, and the alarm is critical, and so it is suggesting us to stop the car and increase the distance. So let us go to PiximLab and increase the distance above 170. Then the red LEDs will be turned off, and we can observe in dashboard that the alarm will be turned off. As we can see, the alarm is turned off. Then let us change the left and right distances. Then we can observe that there is a chance of collision in left and right. Then let us observe here, we can see the alarm is advisory, and in the ADAS bird eye view we can see the left and right distances as 15 and 11. So we need to change the distances so that there will be no collision. As I have increased the distances, we can observe LED is being turned off and the alarm is changed from advisory to none. Then let us change the acceleration and apply brakes. Then we can observe the speed being decreased. Let us increase the brakes 2 more. Then we can clearly observe the speed before was 74, now it is 73, now 72. As we can observe the speed being decreasing, and we can observe in the graph also before was 74, 73, and the graph was falling down, and the SOC is also decreasing because the battery is being in use. That is before the acceleration, when it was high, the battery was being drained fastly, but now we can observe that as the torque is negative, the battery is 93.9 and it will increase by time. Now let us change it back and then increase the acceleration. Then we can observe the speed again increasing. Let us wait. As you can see, the speed is being increased again from 67 to 68, and we can observe that in the graph also, and the SOC is being drained fastly. Then let us see the alarm of temperature, and when I increase the motor temperature above 80 degrees Celsius, here a fault LED, that is yellow light, will be on, and we can observe that the motor temperature here also and a fault signal is on. So we need to decrease the temperature, and we can observe here when the fault is on, the torque is 0 because the motor is not in action. Then when we decrease the temperature to a normal level, then we can observe our torque being returning to normal. Let's wait. As we can see, the torque is being returned to normal. Like this, we have successfully implemented the